Kia ora tātou. In this lecture I want to start by looking at the running time for Dijkstra's algorithm, look at an alternative implementation of Dijkstra's algorithm which leads to some efficiencies, and then we'll develop a proof of the algorithm to see that it really works. Okay, first the running time. The first part of the algorithm here involves setting up a couple of arrays of length n, so that requires order n work. Now in the main loop, we'll loop through this a total of n times since each node turns from white to black. In this inner loop, we're just checking each of the out neighbors of u. So if u has du out neighbors, it requires du work, and we're assuming that we're using an adjacency list representation so we can quickly access each of the out neighbors. The only remaining bit of work we haven't touched on is here, where we need to find the node with the lowest dist. Let's say the work for that is amount A. So overall we have n plus an plus m work, since we've gone through this for each node and we've looked at each out neighbor for each node. So we've looked at the sum over all u for du, and that's just going to be m. Now if we have an array and we need to look through it to find the lowest value, that takes time n. That means that a is n, and we get n plus n squared plus m. And since m is somewhere between 0 and n squared, overall we'll get this form of Dijkstra's algorithm as big theta n squared. It should be clear that we can be a little bit smarter about quickly finding this closest node u, and so improve the running time. Indeed, let's look at an implementation now which uses a priority queue to find the node u with the minimum distance to the completed set at any point. Okay, so here's an alternative implementation of Dijkstra's algorithm, and it takes advantage of a priority queue. Remember that each element in a priority queue is associated with a key, and the element with the lowest key is the one that is the front of the queue. So the lower the key, the higher the priority. Here, the key of each node in the queue is the current shortest path from the source using only black nodes. So as before, we pass in the same inputs, a weighted digraph G with cost matrix C, and a source node S. We start by setting up our color and dist arrays and coloring everything white, except the source node S, which we color gray, and we put in the queue with key 0. So here we'll use three colors. Nodes which we've reached but not yet finished, so are still in the queue, are gray. Nodes we've finished with are black, and nodes we've not seen yet at all are white. So here we are in the main loop, where we'll stay until everything has gone into the queue, come back out and turn black. So at the top of this loop, we find the node at the front of the queue, we pop it off the queue, and while we're doing that, we'll record its key. So we'll call the node at the front u, and we'll record in dist its key. Remember, the key in this priority queue is the shortest path through only black nodes. Now here we visit each out neighbor of u x. So at the top of this loop, we calculate the length of the path through u and onto x. We'll call that length t, and we've got two cases. Either we've not yet seen x, in which case x will be white. In that case, we'll color it gray, we'll push it into the queue with key t. If we have seen x, and x is not yet black, and the cost of the best path to x, which is the key of x, is more costly than this path through u that costs t, then we'll update the best path to x by updating the key of x in the queue to be t, using this decrease key method. Once we've done this for every out neighbour of u, we'll colour u black and we'll get the next node which is closest to the black set S. As you can see, every time we pass through this loop, one more node gets coloured black, and so eventually we'll finish, all nodes will be black. So why do we bother with this implementation? Well, if the priority queue is implemented as a binary heap, well, we're doing n of these operations here, and each operation is going to be log n, as the binary heap is at most n deep, and the rest of our work is going to be down here where we're updating the keys. Each decrease key operation is going to be, well, it's going to be bounded by log n again, and how many times are we going to do that? Well, we'll update keys at most once for each arc, so m times. So we get a bound of big O of n plus m times log of n. And assuming we've got a connected graph, connected digraph, that's going to be m log n. It turns out that the best complexity bound for Dijkstra comes from using a Fibonacci heap, where you can get a bound of big O m plus n log n, which is clearly better than m log n for anything more than a very sparse graph. Okay, so how can we prove that Dijkstra's algorithm actually produces the correct answer? Well, we'll use an inductive proof that shows that nodes that have turned black have found the optimal paths, so that when we reach the end of the algorithm and all nodes are black, we'll end up with the values recorded in dist being exactly the length of the shortest path from the source to every node. So formally, the statement we want to prove is this one. After Dijkstra's algorithm is run on a weighted digraph G with node set V and arc set E and weight matrix C, we're starting at source node S. Then for every node X in the graph, we have that dist X is just the distance of the length of the shortest path from the source node to our node X. To help in proving this, we'll introduce the set S, which contains all nodes that have turned black. Then we want to show that at the top of the while loop, we have that for all X and S, that is for all black nodes, our result holds. So that dist X is just the distance from the source to X. By the time we've been through the while loop n times, so that S will be V, the result will be proven. So we'll use induction on the size of S. Remember, in induction, we first show that the result holds for the base case, here where the size of S is just 1. Then assume that it holds for some arbitrary value k of the size of S, and then prove that this assumption implies that it holds for the value k plus 1. That is when we've done one more iteration and S is size k plus 1. In the base case, when we arrive at the top of the while loop for the first time, only the source node is black. So our set S is just equal to the set containing the single source node, little s. And dist S equals 0, which is just the distance from S to S, so our result holds. Now for our induction hypothesis, we assume that we have been through the loop k times, and each time at the top of the while loop, then we have for each node X in our set S, the result holds. So dist X equals the distance from our source to X. So let's say that the set SK is the set S after we've been through the loop k times. So our assumption is that for all X in SK, our result holds. Now we want to show that after one more iteration, the node added has a desired property. Let's say that node U is the node added after the k plus 1th pass through the loop. So sk plus 1 is just equal to sk union U. Note that we only need to show that U has the desired property, since all other nodes in sk plus 1 are actually in sk, so have the property that we want according to the induction hypothesis and the observation that once nodes are in S, their values for dist never changes. So there are two cases then for U. The first is when there is no path from S to U, which we will see is easy. And the second is when there is a path from S to U. So let's deal with each of those separately. In the case of there being no path from S to U, then we have that the dist for U is infinite, which is the same as the distance from the source to U, and so we are done. The more interesting case is when there is a path from S to U. In this case, we'll show that all the intermediate nodes on the shortest path to U are black, and the result will follow. So since there is a path from S to U, there is a shortest path from S to U, and I've drawn one here. It goes from S to U and has a couple of intermediate nodes, X, which is the last node in SK, and Y, which is the first node which is not in SK, and then it carries on to U. So there are a few things that we can say outright about this setup. In fact, we'll show there's 4 properties that will help us complete this proof. First, let's just write down what we've drawn here. So the first property comes from the fact that all arc weights in the digraph are non-negative. So the distance from S to Y is less than or equal to the distance from S to U. Secondly, we have dist U is less than or equal to dist Y, since U was the node chosen at the last iteration and not Y. Thirdly, we have the relatively obvious property that the distance from S to U is less than or equal to dist U. And that's a property that always holds, since dist U is the length of some path from S to U, and the distance from S to U is the length of the shortest path. Our last property comes from the induction hypothesis and from the update formula. So by the induction hypothesis, since X is in SK, the distance from S to X is just dist X. Now when X was added to S, dist Y would have been updated at this step because it is an arc from X to Y. And it would have been updated to dist X plus the cost of going from X to Y. But this is just equal to dsy, since S to Y is a minimal path to Y. Therefore we have that dist Y is equal to the distance from S to Y. And that comes from the fact that this is a minimal path. So we can put all those things together and write down the following inequality. So by property 1, we have that the distance from S to Y is less than or equal to the distance from S to U. By property 3, that is less than dist U, less than or equal to dist U. By property 2, that's less than or equal to dist Y. And by property 4, dist Y is equal to the distance from S to Y. So since this begins with the distance from S to Y and ends with the distance from S to Y, equality must hold throughout. And crucially, we have that dist U is equal to the distance from S to U as required, and our proof is complete. But how can we have a picture like this where there is this intermediate node Y before we get to U? Well, either we have that Y is equal to U, or there is a zero cost path from Y to U, and it just happened that we chose U before we chose Y. In either case, we've shown that the values that Dijkstra produces are indeed the lowest cost paths to all nodes as required. So we've seen that Dijkstra's algorithm solves the single source shortest path problem in the case that the digraph we're looking at has no negative weight arcs. If there are negative weights, it may be the case that Dijkstra still gives the right answer, but it's certainly not guaranteed, and if it does so, it's pretty much by chance rather than by design. Let's look at a very simple example where Dijkstra gives the wrong answer, and that's because of the presence of negative weights. So consider this small example here, and we'll use our source node will be 0. So we'll initialize, start with that being black, that'll be 0, this will be 1 and 2. At the next step, we find the node with the lowest dist that's not already black, that'll be 1, so we'll color 1 black. We'll follow any out neighbors. It's got no out neighbors, so there's nothing to do. Now we'll choose the only other white node, that's 2. We'll color that black. We'll check any out neighbors, but we'll only update any out neighbors that are white, and we don't have any in this case, so we're done. So we've got an answer from Dijkstra, but is it the correct answer? Well, the shortest path to 1 is not actually across this single arc. If we follow the arc from 0 to 2 and then 2 to 1, we have a path with total cost 2 plus minus 3. So this should not be 1, it should be minus 1. And so we see that Dijkstra hasn't found the correct answer. Next we'll look at the Bellman-Ford algorithm, which solves the single source shortest paths problem even in the presence of negative weights. The cost, though, for running Bellman-Ford is that it takes longer to run than Dijkstra's algorithm does.